Welcome to the video on normal curve properties. Let me get the title up here on the board for us. Normal curve properties. So we've discussed the normal curve quite a bit to this point. We have discussed z-scores and what the central points of this curve are and the percentages between plus or minus 1 standard deviation, plus or minus 2 standard deviations, plus or minus 3 standard deviations. We've covered quite a bit about the normal curve, but I feel like we need to go back and just discuss a couple of the very general properties, that we have here with this. And so let's just, this is this normal curve is happening on the x-axis, and so if we think about this, this is the x-axis here, and if we think about what this means again, this is it's a poorly drawn y-axis, but here's a y-axis, and this y-axis represents frequency, and most often this x-axis is some kind of continuous variable, just over here, continuous variable x, continuous random variable x, and this is going to follow, this kind of normal bell shape that we have, become familiar with. Excuse me. So what we want to do here is we want to discuss what some of these properties are. So I just want to go back just for a moment here and make sure that we understand what this actually is doing. So the normal curve in and of itself, and you won't need to know the equation here, but the normal curve itself follows the following equation. For any y value that you want to be able to find, you are essentially going to follow this equation here. 1 divided by sigma square root of 2 pi to the e exponent negative x sub I minus mu squared divided by 2 sigma squared. So what do we need to know here? We need to know, in this particular equation, we need to know sigma, we need to have our x sub I, and then we need to have our mu. Well, this value here is going to be estimated by this value. This one's going to be estimated by, this x bar value, and this we're just going to plug in from whatever we get, the x sub I, that is. And so we could find this. So for any value x, let's just say x of whatever this value was right here, essentially what we're saying then is this equation, we come up to the line, this equation would give us the corresponding y value over here. This would give us the yi for this particular xi value. Okay, if we knew the mean and the standard deviation that was forming this particular normal distribution. So I just want you to kind of, again, just understand kind of basically what's kind of happening here. This line follows that normal probability function, and this makes a lot of sense here. If you remember even simple graphing, right? If you were just kind of to graph something on an x-y axis, and you want to, if you remember ordered, your ordered pairs, that if you wanted, in this kind of Cartesian coordinate system, if you wanted to, plot the coordinates 2, 3, then this first number 2, on the x here is going to be 1, 2, 3, 4, and let's just say we went up here 1, 2, 3, 4. So this set of coordinates here, 2, 3 would be go over 2 on the x, and up 3 would be this point right here, 2, 3, where this first number represents, how far over you're going on the x, or what's called the x is also called the abscissa, and then the y is also called the ordinate. So the point here is that for any abscissa number here, or x value number on this x horizontal axis, you'll be able to come over here and find the corresponding ordinate using this equation right here. This y is the ordinate, so you're going to plug in the x, the abscissa number, and it'll give you the y, or the ordinate number. So that's kind of the basic formulation of the arithmetic of the normal curve, but it has a couple basic properties, and that's really the purpose of this video. And the first property, or I'll put a bunch of things in the first property actually, but number one is going to be unimodal. That is, you're only going to see kind of one peaked area right here. You're just going to have this one peaked area, and the mean, the maximum height of this will be the mean. So maximum height of this peak will correspond to our sample mean. And so it's unimodal, max height at mean, at mean, it has this kind of bell shape, and it's symmetrical. And I've mentioned this before, but really I just want to hit this again, symmetrical. What this symmetrical piece means is that it's a mirror image, that if you go on the right hand side of the mean to the right and you go into the left hand side of the mean, these are mirror images of one another. Now, the limitations of my ability to draw here doesn't give it an exact mirror image, but you get the concept. So this is the first classification of properties. The second classification of properties is that the normal distribution is continuous. Okay, so the normal distribution, I'll just write ND, normal distribution is continuous. That is, we're going to get a value of y for every value of x. So again, you plug in any x into this equation down here again, into our normal curve, and we can get the ordinate value, the y value. So we'll get a value of y for every value of x, assuming, that is, and I'll just write 3 kind of dots here, assuming x is continuous. So if x is discrete, which it can be, it puts you in a different kind of classification of distributions. And so if we just want to talk about this most simple case here for the normal distribution, then we want to think of x as a continuous variable here. And so what does that mean? This could be age on the x, and then the frequency of age. It could be heights, weights, whatever. These are continuous variables on the x, with their corresponding frequencies on the y. And so the third property here is that the normal distribution, again ND, is asymptotic. That is, the curve, I'm just going to give you another definition, and we'll show you down here on the actual drawing. The curve gets close. This is the definition of asymptotic right here. The curve gets close to the horizontal x, but never touches. This is really important. So if you take here on the right hand side, and I'll just switch to red this time. So what's happening is this curve's coming down here, It's getting close to the x, but it will never actually touch x. So no matter how far out we go, this will just continue to flatten off and flatten off, but there always will be some kind of vertical distance between the x and the tail of this curve. Now what does that do for us? That allows theoretically us to have extreme values going way out beyond 3 standard deviations. So if we were to put those standard deviations in, it might look something like, the mean here would be 0. If we're talking about z's, this might be 1, this might be 2, this might be 3. So you could have a score that's way out here somewhere, way beyond 3 standard deviations, and you couldn't have that if this line came back down here and say touched the x right here. Then the highest value would be constrained to wherever that was. And so the normal curve then has to be asymptotic just to allow us to have these theoretically extreme values. So those are the 3 general properties of the normal curve, and I hope this clears up any ambiguities that you might have. Thanks for watching the video.